Hi everyone, welcome to Huawei Cloud Tech Talk. My name is Danny Chen. I'm a Senior Principal Architect at Huawei Cloud. In the past issue, we introduced the GaussDB high reliability. GaussDB can be deployed in the same CT single AZ, cross AZ, and the geo-redundant mode to ensure database reliability based on the different service requirements. In this issue, we are focused more on the high performance of GaussDB, what problems the customer can meet, and how does GaussDB solve them. GaussDB uses multiple technologies to improve query performance. Let's use the lifecycle application and how we process the query as an example. So first, application send the request to a control node, CN. CN uses optimizer to decide how to process the query. Here comes the first optimization. The optimizer will take a look at the query and figure if there is only data from a single data node. If that's the case, the whole query is pushed down to the execution data nodes. So there is no data change or actual overhead for the network. Everything will be performed within a single data node. In a more common case, the query will access data from multiple data nodes. The optimizer, based on that access pattern, will decide which data node being involved and generate access plans utilizing all of the data nodes. So that comes the second optimization, parallelism. In the centralized deployment, parallelism is done using SMP technology, utilizing all of the CPUs. In the distributed deployment, collaborate all of the data nodes, and depending on the operators, there are several operators forcing the data to be transmitted between the data nodes. One typical one is aggregation, like a group by. Group by itself is expensive, but data transmission is also expensive. Here we take a cost-based decision to decide whether we want to perform the aggregation before the data being emitted from the data nodes. This is called aggregation pushdown. After the aggregation being performed, less data is generated so that we can have less data being transmitted between data nodes. The other type of operator is join operator. GaussDB supports three types of joins: hash join, less loop join, and sort merge join. We make join decisions based on the data volume from two sides of the join table. In the case of one side being really small, we'll use a broadcast decision to send all of the data of the copy to all of the data nodes. In case of two large table join, we will take a relatively small one, build a hash table, and we do redistribute this hash table to multiple data nodes so that the parallelism can be done across multiple data nodes. After all of the execution being done at data nodes, the data node will send the request to the coordinator node. This is called a gather. After the coordinator node gather all the results, it might perform final aggregation before the data is sent back to the client side. So we talk about the key technologies, including aggregation pushdown, including parallelism between data nodes, and how we can make decisions based on different types of joins. We also have smart rewrite technology as part of the optimization. It will try to simplify the query and come out with the simple operations, reduce redundant operations, etc. So next big challenge in the distributed processing is transaction. Historically, GaussDB uses a GTM to serve the transaction management. In the recent releases, GaussDB optimized the algorithm, removing the centralized processing in the GTM. So the GTM now no longer need to send out the snapshot of the transaction state. It only holds a global timestamp, and this timestamp is internally captured at CSN. And when a global transaction comes in, the GTM Lite will send out the CSN, and the visibility decisions will be made by the involving transactions, the CN nodes. So we eliminated the single source of bottleneck. There's another optimization down here. The GTM Lite will not be involved if the transaction is only using single data nodes. As we talked, the transaction will push all of the query, or for this case, to the execution data nodes. so the GTM is not involved. We talk about the transaction management, query optimizer, and the parallelism. Now let's look at the storage. GaussDB provides two kinds of storage for OLTP type of workload. Ustore suits for append-only workload, but for more commonly seen scenarios, Ustore can handle the in-place updates. It's more balanced without significant jittering, even if the services are updated frequently for a long time. There is an independent rollback segment. When data is modified, the data page are immediately changed, and the old copy of the data is stored in this rollback segment. It is used for multi-version requirements. When the isolation level is RC or RR, the transactions can look up the old version through this rollback segment. Comparing to other implementation, the other databases might have to undo some of the transaction to regenerate the older version of the data, which causes more CPU cycles and increases the latency. So the advantage of using this Ustore, first, reduce the overall storage, and it doesn't require the compaction mechanism to recycle the old version of the page. We can simply recycle the rollback segment when the processing state passed some of the recovery requirement. And there is no significant impact to the performance, which means less jittering for the overall system performance. So this brings the storage to the high performance. We are seeing over 10% performance increase using Ustore versus Ustore in the typical transaction scenario by running the TPCC benchmark. And we see less performance jittering using Ustore. And the overall storage efficiency is increased by 15 to 20%. To sum up, GaussDB takes multiple approaches to improve its performance by utilizing the parallelism, by utilizing different storage. We'll talk about another storage in a different session. Thank you.